Okay, hello everyone. Thanks for coming to our research seminar, RAS. And today we have Gustavo Leite talk about Alpa, an automated inter and intra-operator parallelism for distributed deep learning. Thank you, Gustavo.
Thank you, Sandro. Good morning, everyone. So today I'm going to talk a little bit about partitioning deep learning models and more importantly, automatically, and we at least intervention from the user as possible. So the objective here is to present on a high level the Alpa framework. There is a lot of background that I have to skip in order to keep this presentation short, but I hope you learned something by the end of it and about how it works. And so I'll start with an introduction and a motivation as to why we need this. Then I'm going to show you the different kinds of parallelism that exists in deep learning. And then I'll talk about how Alpa decides between those kinds of parallelism, then show you some experimental results, and finally the conclusion. Let's begin with the introduction. So the first point in our motivation is that deep learning models, they have become so big, they don't fit into a single device, and they don't also fit into a single node. So we need better ways to scale these models to an HPC cluster, for example. But experience tells us that programming HPC clusters is not an easy task, and particularly when we don't know what is the best parallelism, best strategy for parallelism in deep learning is. So ideally, we would like to experiment with different kinds and iterating on these different kinds of parallelism manually is a very tiresome task. Um, so we got to a point where even pipelining is not sufficient in the sense that uh, the layers of what a single operator from these models are so large that sometimes they don't fit into a single device. So this is a really it's a really kind of a challenge here. So what the best solution in this scenario is mixing inter and intra-operator parallelism, but it's hard to do by hand. And this is what a lot of research has been done in this area to automate this kind of parallelization. So what is Alpa really? So basically, it's a Python library that runs on top of JAX, XLA, and Ray. So JAX is a deep learning framework from Google. So it's a very different kind of mentality from TensorFlow. I'll probably do a seminar about JAX in the future, but it's suffice to say that it's a deep learning framework written in Python, and you can do some interesting things with it. So XLA is a compiler developed by Google, and it powers both TensorFlow, JAX, and I think there's also other frameworks using XLA. And Ray is a cluster programming model, also based in Python. So they use Ray to distribute the computations of the deep learning model to a cluster. Okay, so the way Alpa works is searches for the best parallelization scheme for a deep learning model using some kind of hierarchical approach. This will become clear in a second. And also executes on a distributed environment, which is really important for us. Not only does it finds the best parallelization, it also executes or distributes the computation on a cluster. So as I said, it's a hierarchical search of the best pipelining scheme followed by the best intra-operator slicing strategy. This is all very abstract right now, but let's keep going. So in terms of motivation, when I say that these models are huge, what do I mean by huge? So for example, we have the G-shard model, which is a transformer model for language tasks. It has 600 billion parameters. We're in 32-bit floating points, we're talking about more than 2 terabytes of only the model. Then whenever we're training such model, we need to save intermediate values so we can compute the loss and actually train the model. So in practice, this 2 terabytes is actually much larger in practice. So this is not going to work on a single machine, like never. So we don't have any other opportunity if not to use a cluster. So there is this switch C, which I don't know much about it, but I know it's a language model as well. So it has 1.6 trillion parameters. So in 4-byte float 32-bit, this is going to explode in terms of model size. Okay, so just to go back to the paper real quick. So this is the paper that I'm talking about. It has been accepted in OSDI 22, but it's available on archive if anyone wants to take a look. And among the authors, there are people from UC Berkeley, AWS, and Google. So there are a lot of big players interested in this, as you can see. Okay, so let's talk about the kinds of parallelism in deep learning. Let's talk about tensors and shapes. So as you may well know, a tensor is basically a multidimensional matrix. And usually when we're talking about images, we use 4-dimensional tensors like this. So the first dimension is called the batch dimensions, is how many images I have in my data set, for example. Then I have the number of channels or number of input features, as they call it. So for example, for an image, I have 3 channels, red, green, and blue. And then I have the height and width of the images. And I'm going to use the example as the convolution here, just because it's easier for me to explain. But everything I'm talking about, a parallelism, works for every operator you can imagine in deep learning. Okay, so when we're doing convolutions, for example, we would like to, we have another 4-dimensional tensor in which the first dimension is the number of output features. How many features do I want to have in my output tensors? The number of input features, which is exactly equal to the number of channels in the image. And then I have a height and a width of the tensor, of the kernel, sorry. And that's why I'm using lowercase letters here to differentiate. Okay, so after I do perform a convolution using this input tensor and these kernel weights, I get yet another tensor which has the same batch dimensions, has the number of output features, and have more or less the same size of the image. Depends on padding and other details, but for our purposes here, they have the same size. Okay, so well, cool. So the first kind of parallelism is a simple data partitioning. So on the left, I have my batch of images. On the center, I have my model. So each of one of those boxes represent a layer or a group of layers in my model. And finally, I want to obtain a measure of loss from this batch of images. So I'm specifically thinking about training. I'm not talking about inference. So training is the harder problem, and this is what we're tackling here. So the data partitioning is very simple. What if I replicate my model exactly in various machines? So I have device 0, device 1, device n. Then I divide my images. So I scatter my batch of images for each device and run them through the network individually, and I get these partial loss values here. Then I can simply do an all reduce operation, obtain like the global loss value for this mini batch, and then do the backward pass for training. Okay, so this works well, and this is embarrassingly parallel. As you can see, there's no communication inside the model here, which is very desirable. But if your model is too big that it doesn't fit into a single machine, you're out of luck. You cannot use this kind of parallelism, unfortunately. So another kind of parallelism is called the pipeline partitioning. Let's say your model is very deep. So now I have A through I layers here. So this is a single model, okay? So it's a little bit different from the last picture. But what I could do, for example, I could assign parts of this model, one to each device, and do exactly as you can imagine, like a pipeline. And this communication here is like a point-to-point communication. So I feed the batch of images to the first devices, and it goes all the way through this maze here, and we get to the loss. And then with the loss, we do the backward pass, updating the weights. So this works well, and you can exploit a very large number of clusters with this kind of parallelism. But as I said, sometimes that is not enough. We need more partitioning. Okay. Another thing to notice here is that this is called the Intra-Operator partitioning or parallelism, because we're not partitioning the layer itself, we're partitioning the model. So it communicates less frequently using mostly point-to-point transfers. So this is a great insight that's going to help us in guiding how we implement Alpa. Okay, so next we have what is called the model partitioning. So for example, here I have my batch of images, and I have my models divided into the several machines or several devices. But now, instead of having the entire operator replicated on all of the devices, I have part of the convolution on this first device 0, then another part on device 1, and the other parts scattered through device until device n, for example. So now, whenever I pass my batch of images through one of the through each of these devices, I don't have I have my tensor is basically divided between multiple machines, right? Um, but what is the problem of doing that? So uh, if my let's say, for example, that my tensor is divided by columns when it exits this first operator, but it needs to be divided by rows on the first operator. Okay, so that's a problem. We need to reshard what is called. We need to do some kind of collective communication to reorganize the data between the devices so we can proceed in our model. So as you can see now, I can manage the problem of memory usage because I'm dividing the operators themselves here. But now I introduce potentially a lot of overhead because I need to do a lot of collective communications inside the model. Okay, so basically at the end we do an altogether because at the end of the model we have partial tensors that we need to combine them and obtain the global loss, right? So in terms of collective communications, there are 4 that are usually employed for different kinds of scenarios. So there's the collective permute, in which you specify a list of pairs of nodes that should exchange information. So collective permute is really useful for exchanging ALOs in stencil computations. Then there is the altogether, in which I have one part of my tensor in each device, and I need to replicate the entire tensor across all devices. So altogether works well here. Then there's the all reduce. All reduce is usually used at the end of the model to sum the partial losses and broadcast the result. And there's the all to all, which is the most complicated and most slow of all, that we can do all kinds of communications. So it's this is the wild card of collective communications, basically. Okay, so there is still another kind of partitioning of parallelism that I didn't talk about, which is the spatial partitioning, as they call it. So now, instead of partitioning the weights of the operators, I can partition the images themselves. So here, I'm slicing the cat, only metaphorically. So I'm sliced on horizontally, so I have the 2 halves, and then I can pass this cat along the model. So in this case, the model is replicated again. So this A here is exactly equal as this A here. So I run the cat through this model, and by the end, I get the loss value. However, if I'm doing a convolution on this image, for example, maybe when the kernel is right on the edge of this image, maybe I need to read something which is on the other side of the tensor, which is on the other device. So at the end of each layer, we probably need to do some halo exchanges here in order to synchronize this edges of the data. And there is also the problems of padding. In practice, it's much more complicated, but it's only to give you an idea of the kinds of parallelism. But there's another insight here. So intra-operation communicates more frequently and using mostly collective operations. So the interesting thing is, okay, so let me talk a little bit about the sharding. How can we divide these tensors? So it's usually done using some kind of they call the device mesh tensor. So I have a 2-dimensional tensor, a matrix basically, and I have this device mesh tensor which tells me how should I divide the data between the devices. So this top left part goes to device 0, then this top right goes to device 2, which is exactly what it tells us. And the interesting thing about this kind of expressing parallelism is that all of the data, model, and spatial partitioning can all be expressed in terms of tensor sharding. It may not be immediate for you, but if you stop and think about it for some time, you see that this is true. So sometimes I'm partitioning the input data, sometimes I'm partitioning the model weights, but they all can be expressed using this kind of representation here. And basically, all of the three parallelism, data, model, and spatial, they are referred to as intra-operator parallelism. And the pipeline stands on a separate category called inter-operator parallelism. So the interesting thing here is that, well, I forgot what I was about to say, but okay. So the inter-operator parallelism, it maps really well to a communication in the nodes of a cluster. So remember when I said that pipelining uses mostly point-to-point operations and less frequently, and this works well if we're using, for example, InfiniBand, which is or Ethernet, which have really low bandwidths compared to something like NVLink between GPUs. So this is really interesting, that, because inter-operator maps really well to nodes, and intra-operator parallelism maps really well to several GPUs inside a single machine. So this is the insights we're using to talk about Alpa. So here we get to the important part of this presentation. So as I said in the beginning, they define a hierarchical search space for parallelism. So we start here with our computational graph. So each of one of those boxes, they represent operators or a clustering of operators. And there is a space of intra-operator parallelism. So imagine that I take this model and literally enumerate all the possible ways I can partition this model. So I can partition every operator by columns like this, or I can partition by line, then column, then line, then column. You can probably guess that the search space is really large. Then there is the space for inter-operator parallelism, which is the pipelining. And again, you could imagine that we're enumerating all of the possible kinds of inter-operator parallelisms in this case. So here we're using 2 stages. Probably in this case, if I have 2 machines on my cluster, I could do put A and B on the first machine and C and D on the second, or I could put just A on the first machine and B and C and D on the second. And you continue here these ellipses enumerating all of those. This is not done in practice. This is just a mental exercise. So what is done usually? Some machine learning and systems expert, it takes a model and manually implement the kinds of parallelism. But if he decides to change this B partitioning from columns to rows, it's going to change the code, and there's going to cause a lot of work in order to obtain this. So you cannot afford to test multiple different kinds of parallelism. So what Alpa does is it defines the hierarchical space. So in the first level, it basically enumerates all the pipeline, the kinds of pipeline, and then inside this space, it basically does a search to find the best kind of intra-operator parallelism. So on this outer level here, they defined a dynamic programming algorithm that searches through the pipeline space, and then they use integer linear programming to search for the best intra-operator parallelism. Okay, so how do we use Alpa? How do we actually use it in practice? So as I said, Alpa is implemented on top of JAX, which is a machine learning framework that uses Python. So basically, let's say I have a function that defines a training step for my model here, and then there's this state.forward. It means like the forward pass on my machine. So the state object encapsulates my deep learning model basically. So I add this decorator, which is called at parallelize. And whenever I call the train step function, Alpa will first generate a representation of this function, execute their algorithm, then compile it using XLA, and then finally, when you actually get to a binary, it can call and it's going to execute on a device cluster. So there's a lot going on this simple annotation right here. And if you're wondering how is it possible to like take a Python function and compile them using XLA, it's because Alpa is built on top of JAX, and JAX has some mechanisms to basically trace this function and obtain an intermediate representation, which it's kind of like LLVMIR. I will talk about it later, which is called AGLO, and the compiler then can run a lot of passes and transformations on this representation, right? So on the right here, there is the architecture basically of Alpa. So the input is the computational graph plus the description of your device cluster. How many machines do you have? How many devices per machine do you have? And stuff like that. Then the first interoperation pass is going to divide the pipeline stages. Then with the stages set, we can go in and decide what will be the partitioning for each of the operators. So if they are gray here, it's because they are replicated, so there's no partitioning. Every device has the entire, for example, the entire weight of this operator. And then with all of this done, we can execute on a cluster using a framework called Ray. So I'm not going to talk much about Ray, but it suffice to say that it is basically a task runtime written in Python. It has fault tolerance. It has a lot of features that we all know about. Okay. Then, okay, so how do we do? I'm going to talk about the intra-OP pass first, and then I'm going to talk about the inter-OP pass. Okay, so consider my model right here. And these are all the possible ways I can shard a matrix, essentially. So the first sharding specification here considers that the data is replicated on all devices. So as you can see, it's gray because 0 has the entire matrix, 1 has the entire matrix, 2 has the entire matrix, 3 has the entire matrix. Understand the devices here like GPUs connected into a single node, okay? Because we're talking about intra-operator parallelism. But I could have some kind of dividing the data both by horizontal and vertically and sending one slice for each of the devices. Or I could have partial replication. So in this case, both device 0 and 1, they have the entire top half of the matrix. Device 2 and 3, both they have the entire bottom half of the matrix. And I could define some kind of one hot vector that encodes which kind of sharding I'm using for this particular vector. So I have this sharding vector for the operator A, and it's have one on the third position here. It means that A is using this kind of sharding here. Okay. So they define this objective problem. This is a integer linear programming in which we feed a bunch of equations that a bunch of linear equations that should be satisfied at the same time, and do a search on the space and find whatever minimizes our problem. And in this case, we're searching for an intra-operator sharding for each of these operators that minimizes the execution time. Okay, so this first term, I have this one hot vector encoding that multiplies the communication cost for a node here. So V is a vertex. You can understand as an operator on a model, and then there's C is the communication cost, and D is the execution cost of this operator using this sharding SV. And I'm just doing a transpose here because this is vector math, and just so the linear algebra checks out here. Then whenever I shard one operator, I might need to reshard it before sending it to the next operator. So there is this resharding matrix R, which defines the cost. Hey, if I have my model partitioned by rows, and then I need my model partitioned by columns. What is the price I have to pay to do this resharding between operators? And this is all pre-computed and saved in this resharding matrix that they call. Okay, so this is vague, I know, but suffice to understand that given this model, they're going to feed into an integer linear programmer solver, and it's going to return what is the best sharding for each of these operators. So S basically here is a matrix. So each row of this matrix represents one of the operators, and each column represents the rows themselves are these one-hot vectors of sharding. Okay. Well, that's basically it for the intra-operator cost. Then I just would like to talk about the resharding cost a little bit. So consider that I have my matrix replicated on all devices. So everyone has the entire data. And I would like to shard this matrix using this scheme right here. So what is the communication cost by going from RR to S0, S1? In this case, the communication cost is 0, right? Because the device 0 can simply throw away the parts it doesn't need and just keep this top half, this top left part of the matrix, right? So that's what's saying this in here in this communication cost. But the communication cost may be non-zero for other kinds of sharding. So let's take the S0R here, for example. What if I have this partitioning and I would like to go back to a replicated scheme? So basically, device 1 and 0, 0 and 1 need to receive this bottom half part of the matrix, and devices 2 and 3 needs to receive the top part of this matrix. So this operation is called an all-gather, in which every player in the communication is going to receive a part of this tensor, and it's proportional to the size of the matrix itself. So this is M right here. And we could do this for every pair of sharding schemes. So for example, if we have something more complex, like if we like to go from S0, S1, which is this one, to S0 on R right here, then we have an all-to-all communication, because those are very different sharding kinds of sharding. So depending on what I choose depending on the sharding that I choose from one operator and the next, I may have to pay this price. And this is all expressed into the ILP formulation that I said before, right? Okay, so let's talk about the inter-operator pipeline. So again, we have our model, and let's say I divide this model into 4 stages. Basically, each operator is going to map to a node, for example. I can run some simulations to get how long does the first operator take, how long does one stage of this operator take, and I can do this for all of those. If I would like to calculate what is the total execution time for this model, I could express it as an equation like this. So I add the latency of all the stages, T1, T2, and T3, and T4, like this. And then I add b minus 1, which is the number of batches, of input batches that I have, multiplied by the maximum of the latencies. In this case, the largest latency here is T3. So, I take b minus 1, so I'm taking this time right here. And if I add everything together, I have the total latency of this pipeline. So we're going to use this equation with a dynamic programming algorithm to find the best strategy for inter-operator partitioning. So the input of the algorithm is a topological sort of the operators from O0 to OK. So we have K plus 1 operators, and a cluster C with shape N times M. So this is basically the definition of my cluster, how many machines do I have and how many devices per machine. And the output would be the minimum pipeline execution latency, which they call T star, right? So basically, we use this F function here, which is basically a divide and conquer style of algorithm. And it tells us the minimal total latency when slicing operators OK OK lowercase to OK uppercase into S stages and putting them on D devices so that the latency of each stage is less than Tmax. So, well, that's a lot of information right here. Let's try to break it down. I'm going to go to the next slide, which I think is going to make more sense. So this is the problem we're trying to minimize. We would like to minimize the latency of the entire model through pipelining. So this function right here, it asks us that what is the latency if I partition this model in S stages uh, from the operator K until the end. So if the first call that I do to this function, I pass the index 0, which means, hey, I want to partition this model in S stages starting from the first operator. And then the D is how many devices I would like to do this partitioning. So at the beginning, I have the entire cluster available. So it's N times M. And I would like to keep this less than Tmax latency. And Tmax, remember, is the latency of the largest operator that I have in my model. So I'm not going to go into a lot of detail about this equation, but as you can see here, F is defined in terms of F itself. So in order to find a pipeline with S stages, first I do a search of a pipeline with S minus 1 stages, starting from part of my model. So it basically tries to find the best one stage pipeline, then goes to the best two-stage pipeline, and it builds up like this. And this T intra term right here is what the ILP is going to return for us. So it's how long we're going to take to execute that particular stage of the pipeline. And okay, so they report in the paper that they do all kinds of optimizations to this algorithm. So they try to prune the search space. They try to cluster the operators in the model in order to feed a smaller graph to this algorithm. In order, this is all to keep the compilation times reasonably low. And you know, it is worth it, because if you have a model that takes 2 weeks to train and you reduce to 1 week, or I know 5 days, that's still a win. So even if you spend 1 hour compiling your model, okay. So well, now we do we ran the intra-operator pass, and we ran the inter-operator pass. We know how we should shard all of our devices, all of our operators. We know how the pipeline stages are laid out. Now I need to generate a binary executable for it. Okay, so for that, it's going to use XLA, which is a compiler developed by Google and powers the TensorFlow framework. XLA compiles down to LLVM. So this is a little bit of off topic here, but basically it defines a set of high-level operations in which it can apply all sorts of machine learning specific transformations, and then lowers it to LLVM, and from there it compiles to a binary. Okay, so this is basically what I said, developed by Google, and the intermediate representation is called HLO, and in HLO there's a lot of operators like conv for convolution, dot, which is a general matrix multiplication, and everything you can think of is defined in this intermediate representation. So Alpa, together with JAX, can generate an HLO from the function that you have annotated in the source code. And this HLO is annotated with the sharding representations that I showed you earlier. I'm going to show an example in a second. So with these sharding annotations on each tensor, XLA can partition the computation and add the collective communication operators automatically. So this is an extension to the XLA compiler called GSPMD, and there's a paper written about it if you are interested. So again, let's bring our figure about the sharding back here, and this is the HLO module generated by Alpa, for example. So I define a module called module, and then an entry function here. So then there's the first parameter. So this function receives a parameter 0, which is a matrix of 24 by 100 elements of F32, which is the data type. And as you can see, there is a sharding annotation right here. So I'm telling the compiler, hey, this parameter that you're going to receive, it's going to come in this format, which is RS0, which is right here. So we're telling the compiler how this data is partitioned across devices. Then you're going to receive another parameter, which is a matrix of size 32 by 100. And the elements are all of type F32. And it is also partitioned by RS0 scheme right here. Okay, so this devices equals a lot of numbers right here. It's basically telling us the partitioning. It's a little bit complicated to explain this, and I don't think this is too important for this presentation. But trust me, this is telling that this is RS0. And finally, I have a dot operation, which is basically a matrix multiplication. So I take my left-hand side and my right-hand side, and I return a matrix of size 24 by 32. And I say to the compiler that the result of this operation needs to be sharded like this, which is in our figure represents the S1R. Okay, so Alpa generates this HLO module and then invokes XLA. Hey, given this module, insert the collective communications in order to keep to partition this computation. So in the compiler, it's actually called partition computation because it's exactly what it does. So it's going to insert probably an all reduce operation at the end here in order to keep those shardings consistent. Well, this is going to eventually be compiled to a binary in which you can happily execute in our cluster, right? So going back to the architecture picture, we can see that each of the pipelines is going to be assigned to a node, and inside nodes we have a lot of devices here, which they call workers. But you can imagine each one of your GPUs as a worker, and it's going to execute in a as fast as it can. And so that's basically the idea of Alpa. I'm going to talk about the results. Okay, so they tested on 3 models, basically the GPT model, the mixture of experts, which is a transformer model, and wide Hesnetch. And we're looking for the blue bars here. So as you can see, it scales well beyond 64 GPUs. So I forget to talk about the graph. So on the x-axis, that's the number of GPUs. On the y-axis, it's the throughput of the computation in petaflops. So using 64 GPUs, we achieve super linear scaling, which is this black box right here. I don't know why they could achieve super linear scaling, but that's what the data is showing. But basically, Megatron LM is a hand-implemented model with all this partitioning. As you can see, Alpa can match Megatron LM throughput very closely, with the difference that Alpa is much simpler to use and doesn't require the programmer to implement the communications and the shardings all by hand. They also showed the inter-OP only and the intra-OP only. If we just use one or the other of the passes, I don't think this is very interesting to look at, to be honest. So then we go to the G-shard Mo transformer. As you can see, when we get to 32 and 64 GPUs, we cannot even run this model because it's so large that it fails. The execution simply breaks down, and Alpa is able to execute it with not linear scaling, but a very good approximation of this. So that's the power of this approach. And the same picture goes for the wide ResNet. With 64 GPUs, we cannot even execute our model. So this is quite interesting. This is a very good result. So here we're showing only the results of the intra-operator partitioning. So forget about the pipelining. Let's focus on a single machine. How does Alpa performs in this case? So again, for GPT, it does comes really close to GPT. Then it continues to scale reasonably well for the other models. And again, much of those guys you cannot even execute to begin with. Well, finally, the compilation time. So, how long does it take to compile a model? So, they take this GPT of 39 billion parameter, and the entire compilation takes 2,000 seconds, which you know it sounds really large, but the amount of performance that you get while training this model, it's really worth it to pay this 2,000 seconds, which is, I don't know, 10 minutes, 15 minutes, something like that. Maybe 30 minutes, but that's okay. So as you can see, the more the larger the number of devices that there are on the cluster mesh, the longer it takes to compile, which makes sense because I have um, more things to consider. More kinds of pipeline, that more ways of dividing my pipeline. And just to show you the end result, this is the wide ResNet with 16 GPUs. So this is what Alpa output. So there are 3 nodes here. So this first dashed box is the first node, then the second dashed box is the second node, and finally the last dashed box is the third node. So for the first two, it basically divided all of the input activations in rows. But the weights, which are the squares here, are all replicated in all GPUs. And the same goes for the second stage, but for the third stage, which the weights are larger in this model, it starts to partition both the input activations and also the weights. So yeah, this is the result. So let's go to the conclusion. Alpa automatically finds the best partitioning strategy for deep learning workloads, compiles this partition model with XLA and GSPMD, and executes on a cluster using Ray and JAX. So the source code is now available. You can find on GitHub. And I think that's it. Thank you for listening to this presentation, and I'm happy to answer your questions.
Thank you, Gustavo. Do we have any questions?
Guido, please.
Thanks, Gustavo, for the very interesting and insightful presentation. Could you please go back to slide 28?
28, here we are.
Yeah. Just to be clear, we're talking about intranode operations, right? So the numbers there represent no GPUs available in a single node, right?
Yes. So imagine that we run Alpa, but only pass a cluster mesh with a single node varying from 1 to 8 GPUs. And so basically, what if we partition our model without using pipelining? That's what they're trying to test here.
Just want to make sure if I understood properly. Could you go back one slide, please? 27.
One slide, 27.
Yeah.
Here it is.
I'm really curious. Okay, so the x-axis here is the number of GPUs in total, right?
Yes, in total for the entire cluster.
For
exactly.
the entire cluster, okay. And I'm really curious to. Oh, by the way, are we talking about 8 nodes and 8 GPUs? What are you talking about here?
So they are running these tests on AWS, if I'm not mistaken, and each instance have 8 GPUs. So if we're talking about 64, we're probably thinking about 8 times 8, so 8 nodes with 8 GPUs.
Okay. So what caught my attention was the first graph on the left, A. As you can see, when you start talking about a larger number of GPUs, and by the way, the larger number of nodes, the intra-operation only speed up is contribution is new, right?
Yes,
the green bar there.
Yeah.
So why is that so? I mean, you have this progression of the green bar coming from 1 GPU to 32, in other words, to 8 nodes, no, 4 nodes, right, on the 32 case. And then all of a sudden, when you double the number of nodes, you add more nodes, right?
Mm-hmm.
8 nodes now, you basically drop the contribution of internode only.
Yes. So I don't remember what they say about this on the paper, but I think it really depends on the architecture of the model, because sometimes if the model is really deep, but the layers themselves are reasonably small, maybe pipeline is going to make more sense. So what it is telling here? So what if we run Alpa only doing the inter-op pass, only doing pipelining and replicating everything inside the GPUs, for example, using the data parallelism, which is the most simple thing that we can do. So basically, that's what the orange bar is telling us. So I think what the orange bar is telling us is that it is worth it to do data parallelism for this model, and we use the pipelining on the cluster nodes. However, if we do only intra-op parallelism, if we try to keep this model entirely in a single node, I think that's what is saying. We don't get much benefit because.
Oh, sorry, I didn't understand now. Because when you say we are talking about 64 GPUs there, that's
Yeah,
the,
no.
the data point, right? So it's not a single node, right?
Yes, exactly.
So what is the distribution of the data, and that you're not using pipelining? Are you replicating the data as many batches there and doing internode operations, internode parallelism? That's what it
Yeah,
means?
I understand your question. I don't know how to answer precisely. I would have to check the paper, but I think that they're just showing these two middle bars here to show that trying to isolate one in the other pass, but in practice we're going to use both, right? So that's what we're
Yeah.
really interested in.
Okay, but the other point regarding this is it possible that when you do pipelining, in other words, you start doing interoperation only, right? And you still talk about the 64 GPUs data point, the orange bar. Is it possible that the communication between the stages of the pipes are so huge for the tensors that you need pipeline to hide that latency? Is it a communication problem that we're talking here? That's why the green bar becomes very low and the orange bar still sustain speed up.
Well, I think it's possible. Yeah, I think it's possible.
Okay.
So
Because
another commentary in terms of pipelining and hiding communication, when they do this this pipelining division of your model, they use the gpipe schedule. So the gpipe schedule tries to divide your mini batch and micro batches, so you can have less bubbles on your pipeline when training this network. So I don't know if they can hide the entire communication, but they do it partly, basically.
okay. And you see the same phenomenon for the intra-operation only happens in graph C, right?
Yes. Mm-hmm.
Okay. All right. So I'm not going to take all the time. So could you quickly skip to slide 25, please?
25, here we are.
Okay. That at parallelize annotation, okay.
Mm-hmm.
You said that Jack's gonna kick in inside each node, right? That's what I understood.
So
The-
when we're executing this driver here, we're not on a cluster yet. So basically, this is equivalent to executing on a single machine, and then when we call this training step, all of this algorithm is going to run and is going to send things to other nodes in the cluster. But when we are defining this function, there's not the concept of cluster yet at this point.
Okay, but my question is a little bit unrelated to that. Is it jitting the whole code with Jax? So what is the role of Jax there? Because Jax would, in principle, do dynamic profiling and not dynamic profiling, sorry about that, but doing like interpret execution till it finds its clauses and then it compiles it. So
Okay.
by doing this at parallelize there, am I saying Jack, say, okay, I'm gonna JIT everything
Yeah. So I get your question. So the role of JAX in this approach is that JAX is going to take this function for us and generate the HLO representation. Then Alpa is going to take this HLO representation, run their algorithm, find and then go back to this HLO representation and annotate with the sharding specifications that I talked about. So JAX is basically a bridge between Alpa and XLA. I would define it like this.
Okay, but it's gonna not JIT, but it's gonna compile everything in binary. Right? It's
Yes,
not gonna interpret part of it, right?
It's similar to the JAX JIT, but it does all of these optimizations before compiling to a binary.
Okay.
Yeah.
All right. Okay, let's go to slide 23, please.
23. So let me go back. Is this 23? Okay.
Yeah, I'm really happy that you said that this now is going to become clear, because for me, I'm going to still need some time to really understand that. But anyhow, what you call the OK to OI operators here, since we're talking the inter-operation using dynamic programming, the operators there are the layers in the model, right? We're talking very high level operators, right?
You mean these OK to OI right here?
Yeah.
So basically, this T intra is our entry point to the ILP solver. So I'm basically taking a slice of the entire pipeline. So from operator K to operator I, please find me the best sharding for this. I'm considering of clustering OK to OI into a single stage. So I'm going to first ask what is the best sharding. And by asking the best sharding, I get the latency of this pipeline stage added to the latency of all the pipeline stages that comes next.
Okay,
right?
okay, but hold it for a while. Okay, the T intra is gonna is basically gonna pass this sub-optimization problem to the IOP solver, right?
Yes, it's going to create all of the objective. I don't know how it represents that internally, but it's basically going to feed this optimization target to the ILP solver, and the ILP solver will give us an answer. So, for example, what do I need to feed to the ILP solver? I need to have this resharding matrix computed. I need to have an estimate of how long does it take to execute each operator. How long does it take to do collective communication for that inside that operator? Do I need to communicate halos? So this all of those costs are modeled here on these matrices and vectors.
Okay, I'm glad that you jumped to go to one slide, please, to 22.
One slide here.
Yeah, no, go back to the 19.
Okay, so here we are, 19.
Yeah. So as far as I remember, JAX uses like kind of a smart round robin scheduler, right? And
well, JAX doesn't schedule. I think you're thinking about Ray.
Oh yeah, I got confused about that. Yeah, how does, because you mentioned Ray very quickly about this, how does Ray plays with this, right? Because if there is a mismatch between the model you do for the inter-operator, right? Because Ray is going to work at the inter-operator scheduling level, right?
Yes. So we take one pipeline stage and put them inside a Ray task, and this Ray task is going to submit to the cluster and execute it for us.
Okay. So when you do the dynamic programming for the inter-operator breakout of the pipeline, it should consider communication, right?
Yes. So in this case, the communication between one pipeline stage and the next is going to be done basically as a dependency between Ray tasks. That's the mapping.
The model, the dynamic program model, assuming some communication cost for that, right?
Yes, it does.
Not here, right? For the inter-OP, if you want to.
So it's the inter-OP. They do consider that. So this I don't like this equation because I don't understand it fully. But they do consider, and they also consider the total memory used So if they find a pipeline stage which is very fast but doesn't fit into that node's memory, it's going to be discarded.
Okay, but somehow it's modeling communication cost there, right?
Yes, it is.
Okay, but my question is, they are estimating communication cost based in some dependencies, right? But the point is that who decides where the task is gonna be is Ray. And the communication cost at the real execution might not match the modeling they are doing here, right?
I get what you're saying. I don't know about how they implemented this, but what I believe is that they do is they do pinning, right? So because when you do this inter-op pass, you know exactly which pipeline stage should go to each node. So they could tell Ray, hey, this task is pinned to node 0, and this other pipeline stage is pinned to node 2.
Okay.
So there is no scheduling basically. Now you just tell where
is the allocation.
What is the allocation. So in this case, it's easy. It's not because the inter-op pass just tell us that each stage should go to a different node, right?
Mm-hmm. So in this sense, it's probably using actors in Ray, right? And not leaving Ray to do what he wants with the schedule, right?
It's possible. It's possible because in Ray, they just so that everyone understands, they divide the tasks into two groups: the stateless tasks, which are defined with Python functions, and the stateful tasks, which are defined as Python classes. And the stateful classes, they can hold state. They can hold, for example, the weights of the operator, while stateless tasks cannot. So I need to check the implementation, but it's very probable that they use actors indeed.
Okay. All right. So sorry for taking all this time. Thanks, Gustavo, for the answers.
No problem. More questions, guys? I know there's a lot of information. This paper touches on a lot of different stuff, but
Any more questions? Anyone? I have one, Gustavo. We have been seeing several different frameworks for speeding up these machine learning models. And you mentioned here Alpa, Ray, JAX, and GSPMD, right?
Mm-hmm. Yep.
So before Alpa, we were wondering where people from Google and etc. were going with GSPMD, Ray, and JAX all being developed at the same time. So do you think that Alpa is the one that comes to tie all of this together?
I believe so. I believe, I don't know if Alpa is going to dominate the world, but I think it's going to serve as the basis from the research here forward. So you're talking about GSPMD. What GSPMD basically does, it understands these sharding annotations, right? But someone has to put these annotations there. Before Alpa, the user had to do it themselves. So I, as a programmer, I look at my model and I think, hey, I think this tensor could be parallelized by columns. Then I put an annotation in my code that's going to translate into this on the IR. What Alpa does is it relieves the programming from that the burden. So hey, write your code normally. Don't write any parallelization directives. Let me find the best sharding. So that's how the GSPMD ties with Alpa. Alpa is basically on a higher level, right? So it just uses SPMD functionality.
Okay, so you actually touched my next question. From what I understood of your explanation, all of the interface between those frameworks are a type of code annotation that one generates for the other to use. Is that correct?
Yes, that's correct. So in practice, in terms of implementation, Alpa, the authors of Alpa, they did a fork of the XLA compiler. They had to change some things in there. I don't think they changed it substantially, but basically adding support to the compiler for their solutions. But JAX is a direct dependency for Alpa because Alpa is going to use JAX to generate this initial HLO that it could then annotate and stuff like that. So it's a very tight integration, I would say.
Okay. Any more questions? So if you don't have any more questions, let's thank Gustavo for his presentation.
Thank you, guys.
Gustavo.
Thank you.